Gabriel runs a WordPress store with one Bitcoin address pinned to checkout. 3 customers pay the same amount within an hour. Which order matches which payment? A Bitcoin transaction carries no invoice field, just an amount and an address. His single address store just broke. The fix is a tree with billions of branches hiding a trap called the gap limit. To fix this, we need a way to name every key in an HD wallet. Lowercase m is the master private key, capital M is the master public key. Everything branches from there. M/0 is the first child. M/0/1 is the second grandchild of that first child. Read paths right to left as ancestry. The rightmost number is the current key. Everything to its left is its lineage. Each extended key can spawn roughly 4 billion children, and the depth is unlimited. Enough addresses for every customer Gabriel will ever have. A prime mark after a number means hardened derivation. Right? Hardened children break the link between parent public key and child, so leaking a child's private key can't compromise siblings or the parent. Normal derivation keeps that link intact, which is what lets us share an extended public key. Hardened levels protect the trunk of the tree. Normal levels let specific branches be safely observed from the outside world. Infinite flexibility is terrible for portability. If every wallet laid out its tree differently, Gabriel couldn't move his seed from Trezor to Ledger to Electrum. BIP43 solves this by using the first hardened level to declare the tree's purpose. BIP44 then defines the standard layout for multi-coin HD wallets, 5 fixed levels: purpose prime, coin type prime, account prime, change, address index. Every compliant wallet walks the same tree, so one seed phrase works everywhere. BP just means Bitcoin Improvement Proposal, a numbered standard. Here's the BIP44 structure. Level 1. Purpose, always 44 prime, identifying the standard itself. Level 2. Coin type, 0 prime for Bitcoin, 60 prime for Ethereum, and so on. Level 3. Account prime, letting you separate funds like a business account from a personal account. Level 4. Change, 0 for receiving addresses, 1 for internal change addresses. Level 5. Address index, a simple counter. Notice the first 3 levels are hardened, the last 2 are normal. That matters because change and index use normal derivation. You can export an extended public key at the account level and generate every receive address without ever exposing a private key. 2 worked examples: capital M/44 prime /0 prime /0 prime /0/2. Purpose 44, coin Bitcoin, account 0, change 0, meaning receive, index 2. And that's the third receiving public key. Indexes start at 0 for the primary Bitcoin account. Second pass, capital M/44 prime /0 prime /3 prime /1/14. Same purpose, same coin, but account 3, Gabriel's fourth account. Change is 1, so this is an internal change branch. Index 14 makes it the 15th change address. Once you read the levels in order, any path becomes a precise coordinate in the wallet's tree. Now put this to work. Gabriel connects his Trezor, a hardware wallet where private keys never leave the device. Using the Trezor web interface, he exports the extended public key, or xpub, for his store's account. He pastes that xpub into BTCPay Server, his self-hosted payment processor. For every new order, the server derives a fresh address down the change 0 branch. Each customer gets a unique address, doubling as an invoice identifier and a privacy boundary. Critical point, if the web server is hacked, the attacker holds only the xpub. They can redirect future payments to their own wallet, but they cannot sign, cannot move a single Satoshi already received. Past funds stay safe on the Trezor. There's a subtle failure mode hiding in this architecture. A wallet can't derive 4 billion addresses ahead of time. Scanning them all against the blockchain would take forever. Instead, wallets look ahead by a fixed window called the gap limit, typically 20 to 100 unused addresses. When a payment arrives on address 0, the wallet generates address 100 to keep the window full. The gap is how many consecutive unused addresses the wallet tolerates before it stops scanning. On a fresh install restoring from a seed, the wallet walks the tree until it hits the many empty addresses in a row, then assumes everything beyond is unused. Here's where it breaks. Suppose Gabriel's store hands out addresses 0 through 59 and nobody pays. Address 60 receives a payment. Gabriel loses his server, restores his wallet from seed with a default gap limit of 20. The wallet scans keys 0 through 19, sees 20 empty addresses in a row, and stops. That payment to key 60 is silently missed, still on the blockchain, still owned by his keys but invisible to the wallet. 3 choices: refuse to generate new addresses past the gap, breaking the store, push past it, and risk missed payments on restore, or reuse addresses, destroying privacy. BTCPay Server sidesteps this with large gap limits paired with throttled invoice generation, a tuned operational trade-off. Step back and see the full picture. The BIP44 tree is more than organization. It's a separation of powers. The xpub is a receive-only credential. The xpub is a spend credential. This same split powers cold storage. Keys live on an air-gapped device or paper, while addresses generate freely on any hot machine. One standardized tree structure makes hardware wallets, web stores, and multi-coin wallets interoperable from a single seed phrase. The gap limit is the quiet operational detail that makes it work in production. Too small and restores missed funds, too large and chain scanning crawls. Gabriel's store now runs on the same mass that secures billion-dollar cold vaults, a tree with billions of branches, a public key that only receives, and a carefully tuned window that keeps every payment visible.